Heading into today's lesson, we are treating wave theory of light. I think in one of our previous lessons, I said there was this assumption previously in science that light behaves as just wave. So I think that's where this lesson will be kind of coined towards, just the behavior of light as a wave. But it's something that's important that we know that light is not just seen as just a wave, and generally matter is not just seen as just matter. So there is what they call wave particle duality. I think it was proposed by Albert Einstein when he was able to predict, or when he was able to prove that all forms of matter and even waves have two kinds of properties. All waves behave like matter. That's what the wave particle theory is trying to state, that all waves can behave like matter, and also all matter can behave like waves. So even us humans, we behave like waves, and we also exist as matter. So, but the reason why it's not easy for people to see how we behave like waves is because, according to them, they said our wavelengths are too large. So since our wavelength is too large, it's difficult for them to see when we are changing frequencies. So for that reason, we cannot notice it. That's the reason why we are seeing like as if we are purely particle. But every single entity that exists, has wavelength and also have frequency. Because what makes a particular entity a wave is its ability to possess wavelength and frequency. Okay, thank you. So as I was saying, I said every entity exists as both wave and particle, and this particular theory is known as the wave particle duality theory. Wave particle
So
duality
don't be
theory.
angry. Sorry. You said what makes
Yeah.
every entity to do what? Can you like go back to what you said before you like talk about network?
Okay, I was saying that every entity behaves like both a wave and a particle. Every entity that exists are said to behave like both waves and both particles. So now, what then can tell that a particular thing is behaving like a wave is its ability to possess a wavelength or a frequency, wavelength and or a frequency. Because if something has a wavelength, then that means definitely it will also have a frequency. So the ability for anything to have a wavelength and a frequency is what can make you call that in a wave. So I believe by now you guys should probably know what wavelengths are and what frequencies are. I just want to assume that, but probably if I go forward in the lesson, I might try to just give a little bit brush up on what these things are. So starting with what I have here, I said wave theory of light proposes that light behaves as a waves. So as I was saying, this theory, the wave theory of light, tries to state that light behaves as a wave, meaning it has both wavelength and it has frequencies. Then also it has other properties that waves are known to have. So I would think you should write that down. So when they say, sorry, when they say light behaves like a wave, it means it has wavelength, it has frequency, and it also behaves the way it has properties of waves. And these properties of waves that they say it has are properties like interference, diffraction, and polarization. Interference, diffraction, and polarization. So these properties, these three properties specifically, they are properties that kind of tell that a particular thing has wave-like properties. So these properties are seen mostly in sound or in sound waves. So they are also seen in light wave. And because of these properties that are seen in light wave, they can tell that light also is a wave because it has these properties. So this theory was um, developed by Huygens and Youngs in the 18th and 17th century. So let's head into the Huygens principle. So first of this Huygens principle states that every point on a wavefront acts as a source of secondary wavelets that propagates outward at the same speed. So at first read of this law or of this principle, it does not make any sense. What is wavefront? What is wavelets? What is the meaning of all this thing that they are saying? So let me try explaining what this principle is trying to state. It's stating that when you have it's specifically talking about light. So say when you have a light source and this light source emits light, that the light would come out of that light source in every possible direction, giving what is called a wave front. That is, if you had maybe a spot as your light source, a spot, maybe like your bulb as your light source, that there would be what is known as a wavefront that would emit, that will get emitted throughout, like from the surface of this light. You know that kind of stuff you see when you have a still water, then you drop a stone, or like you drop stone on top of the steel, on the still water or into the still water, then you notice that there will be like circles living from that spot that the stone dropped in, continuous circle just living off from that point, like emanating from that center where the stone landed. So that circle you are seeing, the edges of that circle is what is known as a wave front. So now, what this Huygens principle is trying to state is that around that circle that is being formed, in the case of a point now, when you have a point like a point light source, you will not see it just as a cycle. It will be like a sphere, because it will be as if from every area of that, so this circle, this is spots like the bulb. Around the bulb, everywhere around the bulb would form a circle that look like a ball, where the light bulb will stay from the center of that circle, like will be at the center of that sphere. I mean that ball. I don't know if I'm making any sense though, but I just hope you guys are probably visualizing what I'm trying to explain. So that circle you are seeing that moves, that goes outward, expanding outward, is called a wavefront. That circle you're seeing is called a wavefront. And now, according to Huygens principle, he said that every point on that circle acts as a secondary source wavelet, meaning every spot on that circle as a new source of light. Every point on that circle acts as a new source of light that is being propagated also outwards. So that's what this law is trying to state, that every point on a wavefront acts as a secondary source of light that is being propagated upward. So assuming we had, now let's assume we are trying to use a single spot light, then the thing emits light, you see a first cycle. It means every point on that circle round can be seen to emit their own circle also round, round that circle. You'll be seeing something like a circular, like circle, continuous circle around that cycle. That's what this law is trying to state. And that this at every point around that initial first cycle, big circle, there is always what is called wavelets. That is other circles that are secondary light sources that has exactly the same speed going outward. So this theory, in normal sense, I think among the laws that we can relate with more, this law is one of those laws that I don't think it's easy to relate with, except probably they are going deeper into physics. So this portion is not really that um, questions don't really come out much like that in this stuff, but just to know what this principle states, because how the questions come out, just they would mention it within an objective question and say, okay, state Huygens principle, or even in your theory. And if you see something like this, you might be like, where is this one coming from? Is this under physics? Just memorize the law. It's not difficult. It's not difficult. Just simple. It says that every point on a wavefront, that is just like as you're saying, every point on a circle can behave as a new source of light that also propagates light outward from their point. That just, if I wanted to put it in simple English, that I would just say it as. So that's what this idea is talking about. So now instead of you saying every point around the circle, now you say every point on a wavefront. Wavefront is replacing circle. Acts as a secondary light source. So instead of you saying secondary light source, you say secondary wavelets that propagates light outward at the same speed. That's just a simple definition. That's a simple definition. So this portion now is trying to state just the properties of this wave, the wavefront, sorry, the wavelets. Say that the new wavefront is tangent to these secondary wavelets. So now what this line is saying is that when you have this circle now, when you drop that stone into into water, you notice that there will be continuous circle that will be coming out of that spot where the stone landed. So they are trying to tell you that when you see circle first, and that circle come. Hello, someone is calling my attention. Okay, So assuming we drop a stone in a still water, you will see circle that will be going out and be expanding. As it's expanding, becoming wider, going wider. There will be another circle that will still start inside and be going wider. Another one will still start again from the same center, be expanding wider. So the distance between these two cycles is said to be like that in between this distance between these two cycles, you will be seeing other cycles in between, constant cycles. So that's what the idea is just trying to talk about. This Huygens principle is just trying to talk about that distance, you can get that distance because that distance is kind of like a tangent to those other small circles. Just take the idea. The idea is kind of a tricky idea, but it's just trying to say that when you have a source, a light source, and this light source emits light outward, every point at the first cycle that was propagated outward has points around it that also emit their own source of light. And the circle that those ones create is what will determine the circle that the next point that's coming out from that same light source is going to be. I don't know if I'm speaking English or I'm speaking gibberish. So that's just the idea. That's just the idea behind it. So you just have a cycle. Yeah. Does anyone have any question? Please just ask me. Probably to help to understand better.
The wavelets.
You said,
I said, can you explain the wavelets?
can I?
Can you explain what wavelets mean?
Okay. Wavelets are the secondary waves that are formed. Like, when we dropped a stone into water, we saw first cycle that continuously expands. That is the wave front. Then when you now take one point on that circle and draw another circle, we've created what is called a wavelet or a secondary wavelet. So now that circle now that is formed, the distance that circles from the edge of that circle is where you will see the next circle, the next wave front will start from. Because when you see continue one circle, another circle, another circle, another circle, that thing continuously move. But now the distance between one of the circle and another circle is kind of like a tangent to one of the circle, the wavelet circle here. I don't know how I want to speak this thing in English to be clear, but just the idea is when you have an initial circle, a wave front, and it keeps expanding. At every point around that wave front, you can also draw circles around it, and the size of these circles around it is going to tell you how the distance between the next wave front that is coming from the same wave source, from the same light source, would be away from that first wave front. I don't know if I'm making any sense at all.
Yeah, it's clear, sir. Thank
So
you.
wavelets are those secondary light sources that are on the wave front. So when you hear wave front, it means that circle, first big circle that starts the wave. The first circle, even the next one is also a wave front. The next one following is also a wave front. So all those circles that come from the main source are called wave fronts. But the one that comes from on top of that wave front, they are called wavelets. Is it clear now?
Yes, sir. Thank you.
Yeah, you're welcome. So now this principle tries to explain how waves propagate through space, and they help us to understand reflection, refraction, and diffraction. So in clear idea, they said this principle is one of the principles that we are responsible for how reflection, refraction, and diffraction, how they can be understood. But if I should go deep into this stuff, if I try to use it, I would need to show it will be higher than what we should understand. It's probably bringing confusion. So when you have waves and they try to bounce on a particular surface, when they bounce, they would start forming a new wave, and that's what is responsible for reflection. You have a circle that keeps on expanding from a circular source. As it touches a surface, that surface will be like a new wave source that will start creating its own new circle and start going upward, and you start seeing something like patterns that are moving. That's how light bounces off different sources. So this is what they're saying. They're saying that the basis for refraction, reflection, and diffraction, the principle that governs this thing, is this Huygens principle. So I think you should just take note of that one. And one of the principles that govern the explanation of or the understanding of refraction, reflection, and diffraction is the Huygens principle. So, so let's move on to our next slide. So I think this is a kind of an extra explanation of what I just was saying so far. So wavelength
Excuse me,
generation. So
sir.
this is yeah, I can hear you.
Excuse me, sir.
Yeah,
Please,
I can
sir,
hear you. Go on.
can we, from your explanation, can we now say that wave front is an initial, that is, an initial front of a wave is the wave front?
Yes,
Okay. Can we now also say that the wavelet is the secondary tangent from that same wavefront?
yes, that's it in simple term. Is the tangent,
Okay, thank
the
you.
wavelengths are secondary
That
from
is, the
or
wavelet is the
secondary,
secondary tangent from a wavefront.
not really secondary tangent, they are secondary wave sources. Not wavelength. It's not
Okay.
wavelength, it's wavelength. LET. It's like secondary wave
Wavelet.
sources. Yeah, LET, not
Okay,
wavelength.
secondary waves.
LET source that starts from the edges
Second.
of the wavefront, from any point of the on the wavefront.
Okay. Thank you very much.
You're welcome. So now let's move on to this wavelength generation. So this one is just trying to explain what I just have explained so far. So
So sorry, please,
um,
can you like repeat what you said? There are secondary wave sources that start from.
that wavelets are secondary wave sources that starts from any point on the wavefront.
Continue, sir.
So that's what I was trying to explain. That's just it. That's the idea.
I know. I'm
Wavelet. I
just
was
saying
trying to
continue with
explain
the
what.
plan. Yeah, I
Okay,
understand.
okay, okay. Thank you. So now this portion now is trying to talk about what I've just been explaining so far, how these wavelets are being generated. So we say consider a wavefront that's an initial circle from a spot moving through a medium. So they say at every point on this wavefront, on that circle, a new sphere or a new circle, wavelet, that's called a wavelet, is being generated and is being propagated also outward. So if you can get us that idea, I don't know. I wish I could show like a circle. Then on that circle, you see plenty of other circles around the edges of that circle. Sorry. So each of those small circles are what are known as wavelength, and they start from points on this first wave front. So that's how wavelets are being generated. They are generated from points on the wave front. So new wave front formation. So now they are saying that the envelope of all these secondary wavelets forms a new wave front. So that's what I was trying to tell you, that the distance. Now you have your initial wave front, then you start having on top of that wave front other small circles. So now the tangent around the edges of all these small circles, this small circle, let's assume this is one of the small circles. If you now draw a cycle around it, the inner points, the edges of these inner small circles is what will tell you where the next circle, the next wave front would start from or would be at. Because they would always be at the edges of this circle. Even when these ones are expanding, they will tell you how or when this new wave front will start from. So the edges or the tangents of wavelets would always give you the new wave front. Tangents of wavelets is what usually give the new wave front. Or would I say inner tangents of wavelengths always point you on the new wave front. So as I said, this principle is what helps to explain reflection, refraction, and also diffraction. So this is just the idea. This is just like an explanation of the principle that I just talked about. So I believe I believe I've done justice to this particular principle, at least to the barest, at least to the minimum level. At least you have an idea of what a wavefront is. A wavefront is that ripple you see. If you just drop a single stone of water, a single stone inside water, the first circle you see, as many things water starts forming that ripple, and it forms the first circle, and you press pause on this life. That first circle you see is what they call a wavefront. Then now, as that first circle will be increasing, you notice that another circle will not form. Why is another circle not form? Because the thing is trying to form, like there's the spots around that first circle would need to form its own wavelength that would expand. And once these wavelengths expand and touch themselves, you would then find the new circle would then be formed. The new wavefront would then be formed from that same spot where the stone got into the water. So we had a first point, and this point started expanding. Then before you know, another circle will start coming out and start expanding. And that will come out again from that same center, expanding. So this is the reason why this thing happens is because of the Huygens principle. Why it does not just happen that you just drop a stone and it's just one circle that just goes round and just stop. Instead, you see several circles will come out from that same spot. It's because of the Huygens principle. And what is happening is a wavefront is creating other wavelets, and these wavelets are allowing for the formation of new other wavefronts. So that's just the idea. So now, interference. So I said properties of waves, or that properties of waves that can make you know that a particular entity is a wave is when it has the ability to diffract or experience interference, and also experience I think I mentioned one of that stuff: diffraction, interference, and I forget diffraction, interference, and polarization. I think, yeah, polarization. So diffraction, interference, and polarization. These are the three things that will tell basically that the particular thing you're trying to look about, if anything behaves in this way, or if anything you know happens to exhibit interference, or exhibit diffraction, or exhibit polarization, tendencies that other thing has wave-like properties. So now interference now is what occurs between two or more waves when they overlap with themselves. So now let me explain this interference in the same idea of we have a water that is still. So now if you have a water that is still, and you took two stones and dropped them into that water at a particular separate distance apart, like some distance apart, and you drop them at the same time and they land into the water at the same time, you notice that each of these spots where the stones dropped would have those begin to form wave fronts, continuous wave fronts. So now when these wave fronts then start touching themselves, the wave front from point A and wave front from point B, we have point A expanding its own circle going outside. Point B is on the other side, so expanding its own circle going outside. So once A and B intersects, those points where they are intersecting is what is known as interference. Because when they start touching themselves, they form a kind of pattern that is looking like net, a kind of net-like pattern. That's what you see when that's what you see when rain is falling. You start seeing something like as if the water is having net throughout inside the water. So those things you are seeing like net, continuous box appearing and disappearing, appearing and disappearing. Those patterns you are seeing is what is known as interference pattern. So that pattern is what is known as the interference pattern. So you would have been hearing of interference in physics, interference. So when you hear of interference, you're talking about the pattern that is being formed when two or more waves interact with themselves, or overlap themselves, or hit themselves. So you form an interference. So now this interference, it's usually from what is known as two patterns: a point of constructive interference and a point of destructive interference. A point of constructive interference and a point of destructive interference. So these points of constructive interference and destructive interference, they have their meaning. So when you hear that there was a constructive interference between two waves, it means that the waves became larger in size at that point, or they became stronger. Let me use the word stronger. They became stronger, as means it was sound, and you had two sources of sound playing music at the same time. There will be a point in that room where if you stand at that point in that room, you will hear the sound louder. It's as if the sound just comes out once. There's a point you will stand in that room, you would hear, or continuously once for a particular very short period of time, maybe something like that, and the thing ceases. There's a point you stand within that room that you will hear the noise louder, and those points where you hear the noise or the sound louder are points of constructive interference. Why the point? According to physics, though I've not really experienced this, and I think the reason why they explained it in one textbook I read, they said the reason why you don't easily notice destructive interference in a room is because of the waves will bounce across the wall, and before you know, everybody, because destructive interference, what happens in case of destructive interference is that those points, if you stand it, as mean you had a very wide room and there are points of destructive interference. If you stand at those points of destructive interference, you will never hear the sound, even if they play the sound very loud. Those points of destructive interference, if you stand at those points, you will never hear the sound. So if we are going back to our net idea, that kind of net idea we are seeing. So those holes of the net, if you stand at points that overlap with those holes, no matter what happens, you will never be able to hear the sound if you are standing in the center of all those holes or those net holes. But if you stand at those points where the nets intersect, you will hear the sound. But there's a point at the center of those square nets or those nets you are seeing where the wave will never touch those points. So those points where the waves never touch are points of destructive interference. So at those points, they are said to be that the waves cancel out each other at those points. I don't know if I'm making any sense to you guys. Hello, can you guys hear me?
Yes, sir, we can hear
Yes, sir, we
Yes,
can
sir, we
hear.
can hear you.
Yes, sir.
you.
Yes, sir, we can hear
Okay.
you.
So that's what this interference is about. So interference, when you hear about interference, someone's mic is turned on, please you just turn it down so that it will not distract. So when you have this interference, what happens is there will be points when you have two waves or two wave sources or two or more wave sources producing waves at the same time. There will be what is called an interference pattern, and this interference pattern is a mixture of points of constructive interference and points of destructive interference. There is points where you've experienced the wave largely, and points where you experience the waves without you will not experience the wave at all. So these points are called points of constructive and destructive interferences. So interference is a fundamental property of waves, and it helps to explain patterns that we see in light and sound. So especially you see it mostly in sound. And I think if we go forward in this lesson, probably you would see how you would notice when or how these things are being observed in light. So let's move on. The double slit experiment, or the Young's double slit experiment. So what this experiment is talking about is an experiment, a scientific experiment that tries to show that light can behave as a wave. That's why light has this interference pattern. It tries this double slit experiment. I think one of the things you should take note from hearing this your Young's double slit experiment is that once you hear it, you should just know that it is the experiment that's trying to prove that light experience or exhibits interference pattern. It's one of the experiments that tries to prove that light exhibits interference pattern. So this how this experiment happens is they would carry a single source of light on one end, probably on your left hand side. Maybe I'll say a single source of light on this side. Then they will put something like a paper at the center. Then they will put a screen where this paper would show, where light would reflect on a screen on this end. So we have the light source, a paper, or a material that is not transparent, a very opaque material. Then we have a what they call it, a screen at the back that can reflect or that can show that something is reflecting on it. So now what happens is that on this paper now, I will not use paper, on this material, this splitting, this material, they would divide, they would make holes, two holes on this material. So then when they shine the light would go through. Some of them will bounce off on the place that there's no hole, but once they pass out through the whole side, the light will come out as circles like this, all those kind of wave circles that we are seeing. And also we'll see the same thing here. wave circles from the 2 points that are open. There's a point open here, there's another point that's open here. So as the light is coming out of this place, it will start coming out as new waves that are forming. And that one too, the same thing start happening here. So now it's now seem like as if you have those same 2 sources of waves. One source here, one of the opening, another source here, the second of the opening. So you then start seeing the patterns moving like this. Then this one too moving like this. So it's now be able to form those points of interferences. So now, once these points of interferences occur, where you have these semicircles intersecting with themselves, the points when they reach the screen, the points where they intersect themselves and they touch the screen, those are the only points you will see lights appearing. Sorry. Those are the only points you see lights appearing, and you something like as if it's something like different. You have 2 slits here. You have 2 slits, but when you pass this light and you give it a distance, the distance between this body and the screen, these double slits are still here. Once the light propagates and reflects on the screen, instead of you to see just 2 marks on this screen, you will see several marks on the screen, several light marks on the screen. And why this thing happens is because of this light wave fronts will keep on going like this. The same thing will be happening here. Then only where they intersect, only the point that they intersect will be the point that you will see light. And now intersect here, you see another light. And now intersect here, you see another light. So that's how you would see a pattern on the screen. That is a pattern of continuous mark. I don't know if you have seen something like that. Probably if you are someone that probably watched science documentary that talk about light or optics, you would have heard about this double slit experiment. So this is how the experiment happens. You will then, instead of you to see just 2 spots, it's just two spots that are here. Instead of you to see just 2 spots, you will see several spots on the screen, several markings of light on the screen. So this is the experiment that is trying to prove that light exhibits interference pattern. I don't know if it's clear. I don't know if anyone has any question. Can you guys hear me?
Yes, sir.
Yes, sir.
No, I didn't really get
So
the
let me bring that.
double slit.
Okay, so
Yes,
you didn't
sir.
really get the.
Yes.
Okay. It's just, I will just tell you the experiment setup and the final result. Then after I've mentioned this thing and you can understand the experiment setup and you can see the final result I'm talking about, I will then explain why the final result happened and probably to give you a clarity on that. So now the experiment setup is this. You have a single source of light, probably a very big source of white light. Then this white light is then turned on. It will go as a very large beam. But now there's an opaque material at the center here. The opaque material is something that it does not allow light pass through it. It's not transparent. So then now, as mean they did not make hole through this opaque material, light will not pass. You will not even, the screen, you will not see any shadow or any light mark on it. The screen is at this end here. You will not see any light that will touch the screen. So now, they now said, let's try what they call the double slit experiment. They now, this material that is here at the center, they now made 2 holes on the material, one hole here, another hole here. So now when they open these 2 holes now, the light is still on. Light would come through, beams of light will pass through this hole, right? The person that said she did not understand, normally beams of light will pass through this hole, right?
Yes.
Okay, and normally since they are just 2 holes, the beams of light are supposed to show just 2 spots on the screen that we have here. But now, what is observed when this experiment is being carried out is instead of you to see just 2 spots that light is shining on, you would see several spots that light is appearing on, several spots. Some places have high intensity, some places have low intensity, but you'll be seeing several spots where light will be reflecting on the screen. So it's not if you don't know what happened, if you're just going to first and what happened? Does this material have other holes I'm not seeing? It's just 2 holes I made, but why am I seeing several spots on this screen? So the reason why we are seeing these several spots is because of light is exhibiting what is known as that interference pattern. So that interference pattern is now that from these individual holes, light would come out as the thing is going from one side, coming on the other side. Instead of it to come out as a single straight line, it will come out as a wave. circular wave. That's that type of thing you see in water. Those kind of water wave. That's how the light will come out as. The second side is also, you also have that same cycle of semicircle going out. So now those points where these two semicircles are intersecting, you find something like net. That kind of thing you see in water. When you drop two stones inside water, you start seeing net, something like net ripples, net-like ripples. So those net-like ripples will keep on expanding. And when they get to this edge of this screen here, the points where the net edges touch are the only points you will see marks. At the only point you will see marks on the screen. So now this thing that happened is what is called interference. So this is one of the experiments that tries to prove that light exhibits interference. I don't know if it's clear now. Well, the lady that asked, I don't know if it's clear now, if you got me clearly now. Okay.
Yes,
Okay.
sir.
Okay, thank you. So this experiment, the reason for those several marks that you see, several light spots or light patterns you see, is because of what is known as constructive and destructive interference of light wave. So the reason why they saw all those several marks or those several spots of light on the screen instead of just two is because of the property of light that is exhibiting constructive and destructive interference or interference generally. So that's the idea of this double slit experiment. So now there is a formula that can be used to tell the distance between these spots you see on that screen. There's a formula, and that formula is what they call it. It's called the fringe spacing equation. The fringe spacing equation. So now this formula is given as this: delta y equals to this expression. This expression. So this 0, 0 that you're seeing here, just ignore it and just take it like as if you are seeing combination and permutation kind of stuff. So the formula, this is the formula for this is the formula. This is the formula. You barely have a point where you use this formula, but just take note of the formula. Okay. So now this formula, it has parameters that the formula, what the formula is used to is used for is to help to is used to get the spacings between those light points you see. So now, as I was saying, the fringe spacing equation is like the formula that tries to tell you the distance that you will be seeing between each of these what they call it, each of these light spots you see. So the simplified way that this formula appears as, you see it as, instead of writing this stuff that is here now, just write on your notes, write delta y equals to lambda, that is wavelength, times capital L all over D. So instead of writing this stuff that is going to look confusing, just write on your notes capital Y, delta Y, this delta Y is equal to lambda, that's this lambda wavelength, times L over D. So that's the simple form of the formula. I think this error, this kind of like was an expression error.
Yeah, please come again.
So the formula for the fringe spacing equation is delta Y equals lambda, that's wavelength, times capital letter L, both of them all over D, where lambda, right, where delta Y is equal to the spacing of the lights, or the distance between each of the lights appearance on the screen. Then lambda is the wavelength of the light. L is the distance between the slits on between the distance from the slit to the screen. That is from the material, that center material to the screen. The distance between the center material and the screen is what is your L. Then your D is the distance between the two spots, the two openings on the opaque material, the two openings, the distance between the two hole is what is your D. Your D is the distance between the two opening of the hole. Your L is the distance between that material, that center material and the screen where the light is being displayed. Then your lambda is your wavelength. Then your delta Y is the distance, that screen that you have here, distance between one of the light spots and that light spot and that light spot. So distance between each of those light spots is what is your delta Y. So that's the interference pattern equation or the fringe spacing equation. So now let's move on to the next property, diffraction. Diffraction. So this diffraction is a different property. One of the properties that any entity that exhibits this property can be said to be a wave. So this diffraction refers to the bending of waves around obstacles or through narrow openings. So it's still the same thing that this is the thing that happens during that during the double slit experiment. Those two openings that we have, the reason why the light could pass through those openings is because light had the ability to diffract. So now we had a large volume source of light coming from this end. So now there was just two holes for them to struggle through. So now they came through this hole and expanded outward. Now we are seeing circular movement outward, expanded outward. So this expansion outward is what is known as diffraction. And when it comes out of this narrow point, it's then expanding. So this behavior of light being able to pass through narrow portions and expand once it passes out of those once it goes out of those narrow sections is what is known as diffraction. Diffraction. So as thing comes out of the other side, instead of it come out as straight lines at that side, it's come out as bent lines, like semicircles as it's coming out. So this behavior of light or this behavior of waves is what is known as diffraction. So now instead of the wave to come out as a single straight line out, it will be as the thing goes through this part, it will then, instead of it to come out as a straight line, then come out as a curved wave, continuously curved wave. So now as this curved wave is expanding outward, it's coming out as a curved wave. That's one of the properties of diffraction, and then expanding outward continuously. So now expanding outward. So the combination of these two, being able to bend and expand outwards, is what is known as diffraction. So the ability for waves to be able to pass through narrow openings. Then when they are coming out, they come out as bent lights, like bent waves, like curved waves, and which expands outwardly to become larger in size. This ability is known as diffraction. So that you can see it in water too. In water, that's what you see when water, instead of water, as you drop a spot of water, we don't see just a single straight line. You see it even when it lands on the wall. So I was saying diffraction pattern, it is when you cannot interference, difference between interference pattern and diffraction pattern is interference occurs when wave fronts from two different wave source interact with themselves. They form patterns, and all those net pattern. So that pattern in that case is called an interference pattern. But now when it is that a wave front is going from a particular source and hits an obstacle and then creates new patterns, all those kind of circle, like when the ripple from a particular water spot hits the wall and start forming another new circles bouncing off from the wall, and you start seeing all those kind of net expression again. Those kind of net expression they are seeing, or those net appearance they are seeing, because they come from they come when this light or these waves hit an obstruction. They are not called interference pattern, they are called diffraction pattern, because they are formed when when these waves hit an obstruction. So once this pattern is formed, they look alike, the two patterns look alike, but the difference is that one of them is formed as a result of waves or wave fronts coming from two different sources. That's interference. While diffraction comes from wave fronts hitting an obstacle, you will see the pattern forming. I don't know if that's clear.
You
Is that
understand,
clear?
sir? Yes, sir.
Okay, thank you. Okay, thank you. So now that's what diffraction patterns are. So they are formed when there is there's an interaction or hit with an obstacle. So now the formula for this is d sine theta, not theta, sorry. This is d sine theta equals m lambda. So that's the formula for the distance between each diffraction that you see. Because once this diffraction happens now, you will still form points of what they call it, points where they are called points that you see kind of that kind of thing that looks like constructive and destructive interference. You see those kind of stuffs. But now those things you don't call them what they call it, you don't call them interference because they are not coming from they do not emanate from interference. They are called stuffs like diffraction grating. So they are called diffraction grating. So from here I said diffraction gratings are optical components with many closed space slits that produces detailed diffraction or that produces detailed diffraction. So this what they call it, when diffraction happens, what you see is what is known as a kind of diffraction grating. So you not call it a an interference or a constructive or a constructive or destructive interference. You see it, you call it a kind of diffraction grating. So there will be points of interference. There will be point of intersection where these two waves they would collide with themselves, and when they collide with where they form those kind of nets, or where those nets, the points where the two ropes or two lines of nets meet, are points where there is kind of like an increased amplitude also. Then the points where they are empty are points where there is reduced amplitude. But now this thing they call this appearance that you see, they call it a diffraction grating. So now the formula to calculate the distance between one diffraction grating and another diffraction grating is what we are seeing here as this formula. D sine theta equals m lambda. D sine theta equals m lambda, where m is the order of the maximum. So usually this m is is usually given in the question. Most of the time they'll give you order as the order of what they call it, the order of, I think, order of diffraction. That's what they call the m, order of diffraction. So you will see it usually when you are given a question, or they might be asking you to find the order if they give you other parameters. So m is the order, lambda is your normal wavelength, theta is the angle of diffraction, while what they call it, d is the distance between each of the grating spaces, or each of the points where the if you should, because if you put a screen also, you would see the same mark on the wall too at specific points. So these points, this distance between these points is what is known as the diffraction grating. So these points are known as, the distance between them is what is known as this d, the distance between the two slits, or this between the slits. So in this case now, we are not putting a slit in between. We just have a wave sent. Once steam bounces off from a particular source, it goes, bounces off, and as it bounces off and goes back to the screen, like as if now you have this obstacle, this wave source, that's this light source, then the screen and behind the light source. The light source here, a point light source that can send light just in one direction. You have your light, these are the experiment look like. You have your light source here. You have your obstacle here. Then you have the screen at the back. So now this light source will send its light towards this obstacle. And this light, as the thing bounces off this obstacle, it creates a diffraction pattern. And where this diffraction pattern then intersects, where they intersect when they land on this screen at the back of the light source, where you start seeing something like mark, that's something we saw in this thing, in interference. You will see that kind of thing on the screen. Sometimes if it's in some kind of material, you see it as colored. If it's white light that they use for the source, you see it as colored, what they call it, like rainbow on the screen. So now, if you are getting the idea of the difference between this diffraction and interference is different when you have two sources. Diffraction comes when the light goes to a source, like bounces off, and as it bounces off, creates a pattern on the screen that is behind the light source. So that's the idea. Those are the differences between the two of them. So now those points, the point that you are seeing on this thing on the screen, distance between them is what is known as the diffraction grating. distance between those points that you're seeing now is what is known as the diffraction grating, or the grating space, or the grating space. So now we have example of where the formula is being used. They said light with wavelength 600 nanometer passes through a diffraction grating with a slit spacing of this. Calculate the angle for the first order maximum. They gave the first order maximum of 1. So now it's just a simple linear equations kind of stuff. You just plug in all your parameters. Once you plug in your parameters, you get your final answer to be just straightforward answer. So the key takeaway is understanding the concept of diffraction and being able to differentiate diffraction and interference. Being able to differentiate diffraction and interference. So once you're able to differentiate these two, I think you are good to go. Does anybody have any question? Can you guys still hear me?
Yes, sir.
Yes, sir.
So we are
Yes,
very
sir.
sir.
Okay. So that's diffraction and what they call it, and interference. So now let's move on to the next one, polarization. So polarization refers to the orientation of the oscillation of light in a particular direction. So this polarization of light is it's kind of thing that happens when light waves vibrate in one direction instead of vibrating in all directions. So that's the simple explanation of polarization of light. Is what happens when light waves vibrate in just one direction. So now I think this is the idea. When you hear polarization of light now, practically now is when that kind of thing that you see during monochromatic light, where they will say, or all these blue screen lights, where a particular obstruction or a polarized material would allow a particular wavelength of light alone to pass through it. A particular wavelength of light alone to pass through it. So polarized material, they are materials that can allow light waves, only a particular wavelength of light pass through. So now, lights, when we allow white light pass through, white light contains all the spectrums of light: red, blue, yellow, green, indigo, violet, orange. That's normal white light, the spectrums of white light. So now, when you now polarize a screen, what happens is that you now restrict the screen from allowing all these other wavelengths of light pass through, except a particular wavelength. So doing this is called polarization. That is by allowing just one particular type of wavelength of light pass through in one direction or in another direction. I don't know if this is clear. I don't know if this is clear. Can you guys still hear me?
Yes, sir, we can hear you.
So polarization is when you try to allow light vibrate in just one direction instead of in all direction, because light vibrates in all direction normally. When you release a light source, it will vibrate in all directions. So when you are carrying out polarization, you're trying to restrict light to just vibrate in just one direction. So any other direction that is different from that direction that is selected, you will not see those light waves. You will not see their reflection. It's only that selected direction that you'll be able to see, or you'll be able to see, that will reflect on the screen. So these tendencies, this behavior, or these characteristics is what is known as polarization. The ability to be able to restrict light from vibrating in other directions or in all other directions. And restricting is just vibrating in just one direction is what is known as polarization. So this is one of the properties of waves. This is one of the properties of waves that you can use to, like now, if probably you guys have heard, you'd have heard, or if you are someone that probably you learn documentaries, even in sound waves, they say whale, is it whales? No, dolphins, they talk to themselves through waves. they send wave signals to themselves. We cannot hear it because our own ear, the human ear, hears only waves between, I think, 20 hertz to 2000 hertz, or 20,000 hertz. That's the only wave, or that's the only frequency that the human ear can understand. Anything below 20 hertz, the human ear will not be able to understand it or be able to translate it. Anything above 20,000, the human ear will not be able to translate it. So it's a selected wavelength that the human ear can transcribe or can understand. It's not that other things that they are, even as everywhere is silent, there are still noise going on, but we cannot hear these frequencies of noise because of our ear is selective. So now this property is what is known as polarization, where you can just restrict other vibrations of a particular wave or other frequencies of a particular wave and allowing just one frequency to pass through. I don't know if that's clear. I don't know if that's clear.
It's clear, sir.
Okay, so let's move on. I think we should be almost done. So this is the idea that we see in what they call it. This is the idea we see in monochromatic lens, where you see that during sunny time, you will notice that the lens will change its appearance, and for only selected light will pass through, and you will not be able to. The light will not be too bright for you. The light will not be too bright for you. So this is the idea that is behind it. This is the idea that is behind it, and I think that's also what happens sometimes when you would have glass and you have water on the ground. You will see just a particular color or some kind of spectrum of light passing at the other back. So this idea is what is known as the idea of polarization, or the property of polarization. So let's go to the formula for this.
Excuse me, sir. Excuse me,
Yeah,
sir.
yeah,
Please, are you trying to say is this same idea of polarization that is behind the mirage effects?
yeah, kind of, yeah. Though mirage,
Okay.
mirage is not necessarily water. Mirage, you're not really seeing water on the road, but what's happening is we are seeing a kind
Yes.
of reflection of light from
Light.
on air,
Okay.
water vapor, on water vapor. So now that reflection is what we are seeing as mirage. It's not that we are already seeing when the mirage only happens when the road is very hot. If the road is not hot, you will not be able to
Yes,
see
sir.
mirage. When
You
the
will not
road is
see it.
very hot. Yeah, that's when you water vapor can be leaving the screen.
Thank you.
Okay. So now the formula. So I think I was talking about polarization. You heard
Yes.
about polarization now. Okay, then the last
Yes.
person asked a question about, yeah. So um there is the formula that can be used to get the angle that is allowed, or the direction that the light is allowed to pass, or the direction of light that is allowed to pass. So that polarization is selecting the particular polarization. They say light always travels in all directions when it is released from its particular source. So polarization is trying to restrict only one direction of light to pass through. So now the ability to determine, or the formula that can be used to determine the angle of light that is being allowed to pass through a particular polarization, is what is known as this Brewster's angle, or that angle that passes through a polarized or a polarizer. That angle that passes through it, the angle of light that passes through, is known as the Brewster angle. The Brewster angle. So there's a formula that can be used to determine the Brewster angle, or the particular angle of light that was allowed to pass through a particular polarizer. So now this angle, the formula that you're seeing here, I don't know why I was having this kind of error in my formulas. I think the rendering of latex I used did not render well. So the formula is actually tan theta b, tan theta b is equal to n2 over n1. Tan theta b, that's theta b is the Brewster angle. Tan theta b is equal, that's theta subscript b, that's small b at the bottom of theta, is equal to n2 over n1, where theta b is the Brewster angle, n is the refractive index of the medium, as you can see here. N1 is the refractive index of the incident medium. Then N2 is the refractive index of the refractive medium. So this is the property that tries to allow for to that allows the proof of that property of refraction. Property of refraction. So now the portion I think we are almost at time and we're
Excuse
almost
me,
done with the
sir.
lesson.
Please, the N2 is
Yeah.
what?
He said
N2.
N2
You
is
say
the
N2 is what?
refractive index of the refracting medium. So now assuming we had glass and air, the incident medium is going to be air, then the refractive medium is going to be glass. You get, so N1 is the refractive index of the air, N2 is the refractive index of the glass when the wave is moving from air to glass. So N1 is the refractive index of the incident medium, while N2 is the refractive index of the refractive medium. So now let's go on to the next or the last portion of this lesson. So the last portion of this lesson, we're talking about resolving power. Resolving power. So this one is talking about the ability for optical instruments to be able to distinguish between two closely spaced objects. The ability for instruments to be able to distinguish between two closely spaced objects. Normally, our human eyes is very, very smart. We can be able to, or someone that has a good eye can be able to look at things from a distance and say this one is closer to me and the other one is farther from me. So this ability or this particular tendency or this particular ability to distinguish between something that is closer to you and something that is a little bit farther from you, the first object, or things that are, let's assume you put your two hands, you cross your two hands in front of yourself. The ability for you to know that one of them is in front and the other one is at the back or is behind, or maybe two people are running towards you and you can tell that okay, their distance is not, they're not at the same distance towards you. One of them is in front, one of them is at the back. So that ability is what is known as resolving power. So it's the same way it is in the human eyes, is also in instruments. And in case of instruments, it is known as the resolving power. So it is usually a property that is of very, very great importance, that is of great importance in microscopes, telescopes, and other optical instruments. So this can help you be able to know when to zoom. So because of that zoom tendency, now you can be able to see, okay, this one is, it will blow out some and zoom in on some, or focus on one and zoom in on and blur out the other one. That kind of thing that you see in an iPhone camera, where you see all those kind of portrait shots, where just the person you're focusing on is one that will be very clear. Then the person that is beside him, very close, but the focus will not be on that person. So this is the resolving power of that camera. The camera has the ability to resolve and focus on just one entity and know the other people that are far from that entity, even if it's just a slight distance. You can put your hand in front of the camera and you see that it will zoom to your fingerprint, while things that are just behind the finger, you would not see them clearly. It would dissolve them, then just zoom in on only the one that you are zooming in. So this tendency is what is known as resolving power. So instruments that have higher resolving power are known to be able to shoot clearer images, like iPhone. It has very high resolving power. If you look at maybe a phone like maybe an Itel phone, if you're trying to, can you guys still hear me?
Yes, sir, we are
Yes,
hearing
sir,
you,
yes,
sir.
sir, we can. Yes, sir.
Okay, so if you have an Itel phone, probably maybe if you zoom to, or you move to the AI cameras level, it might try to distinguish or have a better resolving power, but still you still be able to find out if the thing is even trying to zoom or do that portrait mode, it will shade off some people's face halfway. You start seeing like as if they blind one of the person's eyes with portrait filter or that kind of vignette feeling. They would feel one of the person's eye, and it's just be rough because of the camera does not have strong resolving power. So for cameras that have very strong resolving power, they can be able to trace out the edge of the person and say this is the edge of this person. Anything outside this person's distance is farther from this person that is the focus. So this is the tendency for instruments to be able to zoom in or give clearer image and focus on a particular image. That's what the resolving power is. So in case you see it in past questions, that's what is resolving power? It is just the ability for optical instruments to be able to distinguish between two closely spaced objects clearly. So for it to be able to distinguish that, that's what is the resolving power. So
So,
that's the
excuse
end
me,
of
sir, you said it is the tendency for what? For instrument to do what?
to distinguish between two closely spaced objects. For instruments to be able to distinguish between two closely spaced objects. So that's the end of this lesson. I think this was the experiment. This is the experiment that we talked about. Double slit experiment where we have two holes and light is passing through. So that's just this one here. Then this one was the diffracting pattern that we're talking about. Yeah, someone was calling my attention. I don't know.
Sir, please, can you send us this link?
The slide I sent it on the group already.
I just joined
Because if
this
you go to the
night,
group,
so I've not seen it.
okay, I'll resend it now. So these are the what they call it.
So which ones of
The
the group?
you said
Sir, please, can you provide this
Which one
heading?
of the group?
That
I'm only
LPP,
on this
what
one.
is that?
no, it's a typo error. I think maybe one of all the you are pressing probably the person that was typing this stuff when he pressed the keyboard, he did not know that this thing was typing this extra word. The real thing is just experiment diffraction rating. This was supposed to be like experiment double slit, experiment diffraction rating, experiment polarization. So that's just it, and that's the end of the lesson.
Sir, please, can you send it on the WhatsApp group?
Yeah, I'm trying to do that now. Trying to do that now. Does anyone have any questions so far? Any question? Okay. So immediately after the class now, I think I would send it from my phone because I think my system is delaying. So I'll send it from my
Okay,
phone.
thank you, sir.
Yeah, you're
Thank you,
welcome.
sir.
So that will be all for this evening's lesson. And thank you all for attending this night class.